You're listening to EE Times On Air, and this is EE Times Current. I'm Taylor Marvin. Welcome back to Brains and Machines, a deep dive into neuromorphic engineering and biologically inspired technology. In this first episode of Season 2, Dr. Sunny Bains of University College London talks parallelism, neural net efficiency, and risk-taking with Caltech's Professor Carver Mead. Discussion follows with Dr. Julia D'Angelo from the Czech Technical University in Prague and Professor Ralph Etienne Cummings of Johns Hopkins University.
Welcome to Brains and Machines. I am Julia D'Angelo.
And I'm Sunny Bains.
In today's episode, Sunny is talking to one of the founders of neuromorphic engineering, Professor Carver Mead of Caltech. After the interview, we will be discussing it with Ralph Etienne Cummings from Johns Hopkins University.
Thanks, Julia. It's great to be back here for another season. Carver Mead has had an incredible career that goes right back to the beginnings of the modern semiconductor industry. As well as being a close collaborator with people like Gordon Moore, John Hopfield, and Richard Feynman, he worked with Lynn Conway to start the VLSI chip revolution. Also, with Misha Mahawald, he helped create the field that we now know as neuromorphic engineering. He hasn't only worked as an academic, though, he's also been involved with startups. There are links to his work and some of the specific papers and books we'll be discussing on our website. You can check them out at brainsmachines.net. I met Carver at the Neuro-Inspired Computational Elements Conference in San Diego in April, where he was being awarded the Misha Mahawald Prize for his lifetime achievement in neuromorphic engineering.
So, Carver Mead, welcome to Brains and Machines. I understand that what we now call neuromorphic engineering started with a focus on low-power parallel processing. Can you talk about how that came about?
Yes. In 1965, I had been consulting for Gordon Moore at Fairchild, and they had invented the integrated circuit there. Bob Noyce was the guy who figured out how to do that. So they started making integrated circuits, and Gordon observed that they kept figuring out how to make more complicated integrated circuits, and that becomes an art form. And then they wanted to build more complicated and more powerful circuits of various sorts. And Gordon said, look at what's happening is every year or so, we make one that's factor 2 more complicated. And he made this plot and said circuits are going to become much more cost-effective by doing it this way. And nobody had caught on. It takes someone to point at something and say, look, this is remarkable. And Gordon did that. And at the time, I was fascinated by what was happening. I was consulting with Gordon since 1959 or 60. And he asked me, how small can you make a transistor? If you're going to put more on a chip, you better make them smaller. So I went off and figured out that you could make transistors much smaller than anybody had envisioned, and they would still work. And I had been doing work with tunneling, which is a phenomenon that happens where electrons can penetrate very thin regions of insulator. I had been doing that for 5 or 6 years, so I could tell how long it would be before we ran into trouble. And it was much smaller than anyone had thought. And so I went on a rampage and became a PR person for scaling integrated circuits smaller. And Gordon was popularizing the idea. So between the two of us, I was showing that you could actually make transistors much smaller, and everything got better. They switched faster, they took less power in such a way that the amount of energy per computation got better as the cube of the scaling, which was quite remarkable, and went around popularizing this. I became the evangelist for scaling to smaller dimensions.
And I understand also coined the term Moore's Law.
I was certainly involved in that. I don't ever claim to have invented anything because it happens in conversations with people like you who communicate so well with the public. And I've always treasured the connection with people that can do that, which I admire enormously. But I was certainly involved in that. And I was getting invited to give talks, and that was natural to evangelize Moore's Law and the ever-increasing capability of computation with the ever more complicated integrated circuits. And these were digital circuits at the time. I had never done digital anything, so I was making it up out of whole cloth, which turned out to be an advantage because I wasn't stuck with the standard way of thinking about everything. So in 1968, I launched into my own effort of finding a way to design and get built my own integrated circuit. And I was badge number 5 at a little thing called NM Electronics, which stood for Noyce and Moore. So it was just 5 of us. It was this tiny little group that started this thing, which became a magic thing that became Intel and became the largest and most successful semiconductor company in the world. So I was living through this, and in the process, I had figured out my own way to design these things, because the way they were doing it, they were hand drawing the patterns that form these circuits, and it was crazy. That doesn't scale. And here I was showing that you could make the integrated circuits with millions of transistors. That was a big number then. Of course, today it's a small number, but that was a big puzzle for me. How do you actually make something that has millions of moving parts? It had never been done. And so it was obvious to me that there's only one way to make things that complicated that were still precise, and that was a computer. And so I had to find a way that a computer could make patterns. And it turned out that there was this thing called a Gerber plotter that was used for making precision artwork of various sorts, and had the capability of making very precise patterns on sensitized photographic negative. And you could just write a computer program to generate these patterns. So from whole cloth, I figured out you couldn't design things the way people were doing it with gates and all that, because that would be a very hard computer program to ever get right. But there were ways to do structured designs that you could make sure would be right and were about as area efficient as if you'd struggled for months by hand. So I was all into this scaling of smaller transistors and more complicated digital systems. The thing I encountered was a very common thing, but I was young and didn't realize that it often happens that people are so stuck in the way they do things, and the organizations have been constructed in such a way that people have a very specialized job they do. The way they were doing it, there was maybe 10 different people at various steps of making one of these patterns. And so there was no person that could see the end from the beginning. Once you're set up that way, it's very difficult to change. So I'm not going to get set up that way. So I started making structures that would do higher level functions and then connecting them together. And you could do all that by computer. So you could take the result you wanted, turn that into input into a program that we called a silicon compiler. And it would generate the pattern for the chip that would do that function. And that was a new idea. It was a student of mine by the name of Dave Johansen, about 1966 or 7. So then you could make these vast arrays of computing circuits, and they were all working in parallel. But all anybody could think of was the step-by-step von Neumann computer. That was the only thing they could think of. And I tried hard as I could ever try to do anything to convince people that what we need to do is to use the parallel computation, everything working in parallel. And I was able to convince a few people. One of them was H.T. Kung, who was at Carnegie Mellon at the time. He's now at Harvard, still going strong, wonderful, smart, visionary fellow. And he went and found these patterns of computation that could flow data through in 2 dimensions. So you could have one data stream coming from the left, another one coming from the right, and a product coming out the top. And this was in the 1977 timeframe. And it has just been put to work in, I'd say, 2017, I think, as a way to do AI, as people call it now. It's really neural networks, which involve a lot of exactly that kind of computation. And you noticed yesterday that Terry pointed out a very steep increase, much faster than Moore's law. And the reason is that since 1970s, we have known how to do things vastly more parallel than they were doing them. And nobody paid any attention until they realized it made no sense the way they were designing the chips to train these networks. And that NVIDIA got on it using H.T. Kung's idea for graphics. And so the graphics processors got to where they were getting more parallel. And then those got to being used to train neural networks. And it was really only because of the parallel processing on chips that we ever got to the point where they could be at a scale which would work with the scale of data on the web and the kind of backpropagation programs that have been around since the early 1980s. So I spent the 70s being frustrated that nobody would go off and do parallel computation to do what's obviously possible. So in 1980 or early 81, I had 2 friends, Richard Feynman and John Hopfield at Caltech. And one lunch I was venting my frustration that there must be paradigms for parallel computation. And I said, what about what happens in brains of animals? Well, yes, that is certainly a known parallel computation of massive proportion. And it obviously does useful things. So why don't we look into what that's all about? So we decided the 3 of us would teach a course, and we'd take turns giving lectures and arguing about things. And we did this course, which had no plan except to explore that space. And the students were a bit bewildered by that course, but the most adventurous students got totally jazzed because this was the leading edge and they could feel it. And one of the students that showed up was a freshman by the name of Misha Mahowald. And she got totally into it. She was a biology major, and she had been working on vision and was just reading all the literature on retinas and how they were wired and trying to imagine what was going on in that wiring. And so she joined our group and was teaching me what she was learning about the retina, which was great because she was learning it firsthand herself and then sharing it with me. So I got jazzed about it, and the 2 of us basically hatched this business of, well, it's said the best in her thesis. If you have a theory, you don't really know if it's right unless you can make it work somehow. And these things were complicated enough that simulating them on the computers of the day were hopelessly slow. Doing it on a circuit where you could make a real physical object that did some version of what you were thinking the retina did. The retina really is a little outpost of the brain right up on the image plane. And there are many good reasons for putting a computation in the image plane because you can do it all in parallel. Well, that was what I was looking for, was something you could do all in parallel. So it was really this freshman who had come to the course that the 3 of us put on and had the sense to say, hey, here's a thing that we know a lot about, the inputs and outputs, but we don't know how it does it. And we could become clear about how it does it by making something that does that. And that was the beginning of the whole thing.
When Misha proposed these experiments, was that the first time you started building circuits to specifically emulate neurons?
Absolutely. It was Misha teaching me about the retina and saying, isn't this a thing that does parallel computation? And yes, of course it was. And it was partially analog, and then it had these digital outputs.
So between the two of you, you recognized that you knew all about the circuits on the one hand, and she knew the biology and was learning the circuits from you. And so she started to see, well, wait a minute, these look just like what I'm interested in over here in the biology?
Well, it just came up out of us talking, and she was telling me about the retina, and I'd say, well, doesn't that mean it's a resistive network? Well, yeah, I guess. So then we try to figure out how to make one, and there was quite a lot known ever since Helmholtz and those people observed what the thing must be doing, but had no real idea how. Wonderful time, really wonderful time. So yeah, it's just the two of us, just, digging in, and it's not something that one person could have done.
So you just won the Misha Mahawald Prize for your lifetime contribution to neuromorphic engineering. Obviously, you started the field together with her. What does that feel like from your point of view?
Well, from my point of view, it's an opportunity to reinforce the role that Misha played in starting the whole field. The people that were in the group when this was happening were very well aware of her leadership position in the group, but from the outside, it hasn't been as obvious. And I think the work that Toby and Shichi and Terry have done in creating this prize is wonderful, and it gave me a chance to reinforce her leadership position in the founding of the field in a way that nobody else could do, because nobody else was there at the time, so would only know what was happening quite a bit later.
So you're generally credited with not only inventing, with Misha, the field of neuromorphic engineering, but also the term neuromorphic. Now, you and I spoke yesterday, and you said that that's not the case as far as you recall. Do you remember where the term came from?
I absolutely don't remember. I like the term. I think it's a really good term. John Pierce had a saying. He said, it was my idea the first time I heard it. And I think it was that way for me, that I don't remember, but it was certainly a term that I adopted very eagerly when it bubbled up somehow.
It's a very good term, and I have to say I felt the same way. It's very evocative of the field. So one of the things that's been argued about a lot over the years is what the key features are of neuromorphic systems. Obviously, in your book from, 1989, Analog VLSI and Neural Systems, you talk about subthreshold spiking analog electronics. Obviously, we've talked about parallelism. What do you think are the features that make a system neuromorphic or not in 2024?
Well, it's clear that the field of neural networks, as it evolved at the time in the 80s, it was not at all clear what approach was going to become matched to some application in the real world. Neural network is a conceptual definition of signal flows, and terms get added together, get multiplied by a weight, and then become part of an output which has some nonlinear function, and then there's another layer, and basically a pretty simple idea, much simpler than anything that goes on in the brain, but was getting results. And the breakthrough was backpropagation, which was a way of allocating blame if you didn't get the right answer. And I guess that wasn't obvious until Hinton and Robelhard and those guys came up with this idea, and then it became obvious. Like all good ideas, they can become obvious once they work. And so that has gone on, and that was neuromorphic in the sense that it was a way of having neurons, conceptual neurons, which gathered inputs from many sources and weighted their effect and put out outputs and had a way of learning. And learning is an important aspect of anything in a neural system. It's only one aspect. The way of agglomerating inputs from many, many, many sources. So the neural networks have been the overall rubric of making things with many inputs and learning. And that went on largely as a computer algorithm. And I was, of course, very frustrated because you take this inherently parallel thing and you then go at it one step at a time. A complete idiotic waste of time because you have all of the silicon there that's holding the weights and holding the data and you're doing it a step at a time. You're going way off into memory someplace and getting one thing and going way off in a different one and bringing them together and multiply them together. And you go off and do it all again, a step at a time. It's crazy. So I was more and more frustrated with this. But it was 2017 or so. It really started with Alex Kraszewski, a grad student of Jeff Hinton's up in Canada. He had a vision that if you had one of these chips that did this kind of operation, and you could get the whole network on the chip, so you'd have to be going off into memory and pawing all around and getting data and putting it back, and which takes most of the energy and most of the time. And he got that part. And then he saw that this one chipset that NVIDIA was putting out, he thought he could put the whole network on that chip. Everybody else were just using some language to go and program. And it was just from a energy efficiency, computation efficiency, it was a mind-numbing approach that everyone was using. But Alex went off and got down in the bowels of the thing and figured out what was really going on and how to arrange things so you'd have to move the data around so much. And there's at least an order of magnitude, maybe 2 or 3 that he gained by doing things in that very compressed, very efficient way. And it blew everybody away. So then people got it that, yes, you had to do more parallel hardware and you had to be efficient in the way you arrange your network. And so that one young man really broke through to what it means to have something that scales. And then, of course, once somebody has done it, then the thundering herd comes along, and now everybody is doing that. And we have available a new paradigm for computing, and it is neuromorphic in some sense. But it's still being done digitally. And this inherently analog thing of adding up inputs and thresholding them in some sense is a very analog thing. And yet people keep doing it digitally and using huge amounts of power and huge amounts of hardware. And you heard yesterday that it takes $100 million to train one of these networks. Well, that's not a sustainable thing, but it's the beginning of a learning curve. And learning curves have this property that they come down in cost and energy and all. Moore's Law was one such thing, and now there's this neural network thing, which is now useful enough and creates enough value that it's worth people's time and energy and invention. So what's coming together is the need to do this better and the resources to support new ways of looking at it. Well, the new ways aren't new ways. We've been at it since back then. I thought that the most obvious one was the parallel processing that happens in the retina, because that's what Misha had figured out and we had done together. And obviously, you get a huge amount of efficiency by sending over the optic nerve the important information, not just copies of the image all the time, which is what people were doing with old-fashioned television. And people were so stuck with the image view of vision that they couldn't get this thing about, no, it isn't the images that are important, it's the action. It's the events in the image that are important, not the image itself. Your eye sends the important information, the edges and the movements and those things back to the brain, and the brain puts them together into what you experience as an image. It isn't what your eye sends to your brain. It's created in the brain, like Misha said so eloquently. That idea is so foreign to the way people have done imaging from down the years. Misha, for her thesis, did the first event-based retinas, along with a lot of help from her classmates. The idea of doing an event-based vision system got to be a way everybody in the group was thinking, and so everybody was doing their own contribution to that, and people were making very sophisticated different ways of encoding things happening in the image plane, and that was the analog to digital transformation that happens in the retina, and it results in nerve pulses on the optic nerve. So there was a tremendous amount of information that was known about what kind of decoding happens in the retina, and that was why it was such a good example to emulate. But it's taken until now, before self-driving cars, that have necessitated doing a better job of vision, meaning what's important in the image. So that's now become commercial, still not huge scale. So it takes that long to get even the most obvious examples of doing it efficiently. But now that the neural network people are up against way too much power, way too many petaflops, now they're starting to get to where they're open to more innovative approaches to that.
Do you ultimately believe that these deep networks will become analog at some point, that will solve analog problems of variability and perhaps thermal issues to be able to create commercial analog networks?
That's an excellent question. I mean, we have a way of fumbling our way clumsily into training these things, but of course, once it pays to do it better, now there's the energies of many extremely bright people looking at this as an opportunity to create value by doing it better. And my guess is that it won't be just a copy of backprop. There'll be that, and that's happening. I mean, once you have the thing going, then people are working hard to make it better, and it's backprop with lots of better implementation. Now, that, of course, will happen because there's pressure to make it happen. But there's also then creates a opportunity for people to think about the whole thing in a better way. And there will be another close look at what brains and the optical paths in brains do to understand images, understand things in the world as encoded by retina-like sensors, and that's going to be a thing of its own. I suspect there'll be something more interesting than just backprop, that there will be a plurality of approaches to learning and training and all of that.
And on the hardware side, essentially what you're saying is that now that people have an incentive to solve these problems, the problems will get solved because the resource will be put into it. So you've done many neuromorphic projects over the years, not just at Caltech, but also at companies like Foveon and Synaptics. Can you talk about one or two of the projects that you did that you're most proud of?
So when Toby was a grad student and we were making silicon retinas, he noticed that if you made the photoreceptor out of different layers in the silicon, you got different wavelengths at the peak of their response. So he said, why couldn't we make a color sensor just with the silicon? Well, at the time, I had been a founder of Synaptics, and that was going along well. So I was interested in the photosensor thing, so we actually spun out a joint venture between Synaptics and National Semiconductor because they had a silicon fab that we could use. And we thought that was a good idea. It turned out to be a very bad idea, but you don't know that till you're into it. And so we started working on Toby's idea, and we started Foveon. We had some really good people there. Dick Lyon was there. We had a very good fab guy. And we were able to make wonderful color sensors. And that project resulted in the best color images that had ever been captured by any technique. We had photographers who were in love with our sensors, and we made a deal with Sigma, who had been making lenses for other people's cameras. They made a lens for Canon and a lens for Nikon, and they had just decided they were going to make their own camera to go with their lenses. They could integrate it better. And we had a good fellow in our marketing. And there's this big thing in Europe called Photokina, which is the largest trade show for imaging-like things in the world, at the Cologne Messe, which is a huge exhibition center in Cologne, and attracts all of the leading companies that have anything whatsoever to do with imaging. And one of them who would be there was Sigma. So our marketing fellow had made an arrangement for me to meet with the man, and we had scheduled a half-hour meeting. So I had our first results from this silicon-only way of doing color, which we called X3. So we spent 4 hours in our half-hour meeting and really hit it off. We were same generation on opposite sides of the U.S.-Japan war. And as we decided to do business together, we formed a friendship. And we thought it would take a year for us to do the imaging side and them to do the lens and camera side and integrate all that. And it was the biggest disconnect between an old-fashioned Japanese, infinitely precise, infinitely careful, infinitely thought through what makes them so good at optics and semiconductors. And of course, here's a Silicon Valley startup that has go for broke. And we both had mutinies on the two sides, but we kept our cool, and we ended up with successful cameras and making some of the best color images that had ever been captured. And I'm very proud of Toby, and Dick Merrill was the fab person, and Dick Lyon was the person that put the whole image processing thing together in his head and got it to all work. And that group of people was very much like the group of neuromorphic people that I had in my Caltech group. But it was fantastic. It was one of those things that eventually the only people that were using the technology was Sigma, and they had a successful camera line. And so they eventually acquired Foveon, and it's now part of Sigma, and as far as I know, still making top-of-the-line color cameras.
So the premise, what made Foveon different, was that essentially you understood, or Toby figured out, that different colors of light will propagate through different distances within the silicon.
Absolutely.
And so then you could put detectors at different layers to pick up each of those different colors.
Yeah, exactly.
So you didn't need to have little pixels that were spatially separate from each other.
Exactly.
You could stack them on top of each other, and then you got this very high resolution.
Yes, and you didn't have the confusion between the location on the image and the color. which was the aliasing that happened with every color imager, and made up a pattern, a circular sweep of color, detail, and angle. And he went around at Photokina and got all the other color cameras to take images, and of course they looked horrible because there'd be some angle where it would catch the aliasing just wrong. It was an exquisite experience technically. I lost money on it, but it was an exquisite experience of technical innovation.
So I know that in the present, you're very interested in dendrites as one of the ways that the field may make progress. Now, I know this is something you're not actively working on, but you're following some of the work by former students and other colleagues. Would you like to talk a little bit about why you think dendrites could be important?
Well, of course, this was my talk yesterday. The dendritic tree does the aggregation of information from hundreds, sometimes thousands of inputs, and extracting from them an important outcome. So they're coming in as events on a bundle of nerve fibers and synapsing on to different parts of the dendritic tree. And we've known for a long time that the dendritic tree has gain because the little pulses from the inputs further out end up growing as they come down the dendritic tree towards the soma, where they turn into a outgoing nerve pulse. So if you just think about it for a while, this is a system that works over orders of magnitude of data rates, all the way from a few incoming pulses giving an output to almost a continuous analog signal based on many, many, many inputs over many orders of magnitude. And that means that it has an ability to distinguish arbitrary subsets of the input patterns that are relevant to the output. That's a extraordinarily exponentially competent computation, obviously important for any kind of living creature to be able to abstract a complicated image or complicated combination of image, sound, and body movement to respond very quickly to inputs of a complicated sort and get extremely important, timely action, which has kept us alive down through the evolutionary past. And so having as a primitive the ability to do arbitrary subsets of groups of inputs over a wide range is an extremely powerful computing paradigm. Does not exist as a computing paradigm in today's world. So what we're doing, we're pawing over the thing and trying to find particular parts of it. We do it by training these things with these clumsy backpropagation things, and the nervous system has figured out a much more efficient way, not only to recognize a thing, but to learn the combinations. And we don't understand how that happens only very broadly. And it's clear that if we had it as a computing paradigm, people would figure out all kinds of wonderful things to do with it, because it's only recently that people are doing computations that are relevant to real-time existence. And that's been largely because of the autonomous vehicles, where you don't get to grind away and paw through all kinds of irrelevant stuff to try to find some little thing that's relevant to a person in front of you in a way that doesn't show up in your training set. And you will never have training sets that have all of the elements of surprise that you have in real life, because that's a set of measure zero, as they would say in statistics. And somehow the way the perception and signal processing works in the brain, it picks out preferentially those elements of surprise. And in my 1990 paper on neuromorphic things, I give a little model of how that can happen. If what you do at each level of the nervous system is you have a set of neurons which is predicting from the inputs what's going to happen in the next little bit of time. And if you get it right, you don't send anything on up because it's not interesting. You've already predicted it at this level. You don't need to send it to a higher level of perception. So if you think about the nervous system as a layered hierarchy of representation, which it must be because we have things we talk about at the level of human experience, there's many, many levels below that. For example, at the retina, the model predicts that the image be uniform and not time varying. And so if it's like that, it doesn't send anything. Whereas a television camera would keep sending all that data, one frame after another. They don't send anything. But if something changes, you didn't predict that, so you send it up. But those are the interesting things. So you sort at every level. You sort for the stuff that's mundane, and you sort, oh, that's different, that's interesting. So as a species, all the way from the elementary forms of life, they're able to survive because they can sense things that are different. And that is a way of thinking about levels in the nervous system, which I put in that paper. And it's also a way of learning that's much more effective than sending the same old stuff over and over and over and over again. And so having a system that does that would be a much more effective way of dealing with things like autonomous vehicles. And there hasn't been an urgent felt need. And I know 10 years ago or so, people were starting to talk about these autonomous vehicles, and they oh, isn't that exciting? And I said, don't hold your breath. And the reason I said that is that it's a much harder problem than people realize because it's a needle in a haystack problem. And so you need a needle in a haystack finder as part of the system at every level, or you're not going to find those if you're just looking at the whole thing. And that has, of course, turned out to be the case, that the standard training, you use this enormous amount of money, energy to train up these networks, and you don't find the needles in the haystack because a system is not built on the premise that needles in a haystack are what we find interesting and therefore spend our neural energy doing.
So you see the dendrite as having a critical role in helping to identify those sort of novel circumstances.
Absolutely. And it's built in, and the nervous system doesn't distinguish gain control from signal processing. It's all part of working over a wide range of density of information and sorting out the parts that are relevant and having the rest of it ignored. And therefore, there are visual optical illusions that land on the fact that our visual system and our attention system and all are looking at the differences. And we can fool a system by concocting artificial images, having the differences, the unsuspected parts, be not the part that's interesting. But in general, we survive in the real world by having the system work the way it does.
Now, you've worked with people of all ages, including a lot of young people over decades in commercial settings and in academic settings. And I wonder if you had any advice for those young people coming up in neuromorphic engineering who are looking to find a niche for themselves and wondering what progress they're going to see. Should we stay in this field? Should we go into something that's immediately commercially hot?
Well, it's very exciting being on the leading edge. There are downsides to it, of course, because you might be a part of the leading edge that'll lead you off in a direction that turns out to be a cul-de-sac. But even so, being on the leading edge is exciting because you can think differently. You don't have to just memorize everything everybody's done, and we do it this way because it works, and blah, blah, blah. So for the young people like Misha, who could see beyond just the grind that has been developed over many years, much of which is brilliant, but it's also well ingrained in all of our education system and in all of the ways companies are organized and so forth. And it's rewarding to make things that work and satisfy the needs of people and to continue to evolve that. But then there are the places where there's real opportunity, and those are also the most risky. So if you don't like risk, you don't go there, because it can turn on you. I mean, I gave you the example of a technology which is still the most beautiful way to capture of color images, and ended up being a difficult and not very rewarding thing for the people who developed it.
Not rewarding from a financial point of view.
Right.
But from what you said, it was very rewarding from an intellectual point of view.
We had the blast. We had a wonderful time. Still a wonderful memory of those of us that went through it. So that's one of the lessons that in the old Silicon Valley, before it got taken over by the New York financial types after the 2000 crash, but up to that point, it had been a place where if you had been through one that didn't work out, that was considered a plus because you learned a lot. And therefore, you could find a spot in a new one that was going in a new direction, because the point was to learn, to have both kinds of experience. The people that very often have the worst influence are those that hit it big the first time. And so they think that they're brilliant because they happen to have got on one that went through. And you can't tell ahead of time if it's going to go through. But even if it doesn't, you learn a lot. You learn a huge amount. You have a great time. And you may not become financially independent on the first one, but sooner or later that'll work out for you if you keep at it. Yeah, but if you don't like risk, if you don't like uncertain outcomes, then don't go there.
So one of my views on this is that you should focus more on being true to your own intellectual interests, as long as you can make a living, right? Which
Absolutely.
Most talented people can do. As long as you're true to your intellectual interests, you'll always be happy. And that will be more important in the long term than having a big house or a swimming pool.
Yeah. I wouldn't say you'll always be happy. Being on the leading edge means that you'll try a lot of things that don't work. And it's always easy to think that's a failure. But actually what it is it's an opportunity to learn. And it's very hard in our culture where we're taught, no, there's a right answer. There aren't always right answers that have any relation to what people think. And we may be on a track that has a right answer that we'll find, or we may not find it. And we may go down routes that have a dead end. And the only way to find it is go and see if it goes through or not. And if it goes through, that's a big high. If it doesn't, you spend a lot of time scratching your head saying, what in the world is going on? If you realize this is the learning process, then you're okay. But you can't help but be down when that happens. I mean, we're human. We really wanted it to work and it didn't. So there's a combination of real world application and a level of reaching beyond what's known You have to be close enough to something that works that you can tell by doing it and making it work that you actually did something real. And a lot of science does make-believe problems, and it's easy to fool yourself that you're making progress when it's really a game. It's just making up things just because you can. Sabine Hassenfelder has a recent, very, very important YouTube thing about her own experience with the game side of science, that you just keep doing these things and writing these papers, and they don't really go anywhere, but you can make a living that way. And after a while, you realize, maybe like she did, that this is just a game. I don't want to spend my life doing this. For people who really want to make new contributions, it's not satisfying. Mm-hmm. So you have to find your own way of being in the world. And not all young people that have the stamina and ability to live through what everyone would think of as failures on the way to figuring out a new thing. Because if it's really new, there will be many false moves on the way. That's part of the learning. And we're not assured it's going to come out the other side. And you have to learn from that and be willing to do it again without the assurance that it's going to come out the other side.
So it's about resilience.
Yeah. And it really helps to have people. I've been so fortunate to have people like Dick Lyon and Misha and Dick Merrill and these people who are right at the edge and just so good at what they do. And also know all of the background so you don't violate known stuff. But you know what the edge of the known is, and that's been an important part of just staying whole as a human being, that you have the friendships of these people who are supportive of a life on the edge, which, you know, there's downside more than there's upside for many periods.
So it's about doing your homework and then being able to push back into the edge and not be afraid to, as you say, go down some wrong avenues while you're there.
Push ahead, yeah.
Carver Mead, thanks so much for coming on to Brains and Machines.
Great to be here.
Thanks, Sunny. So first of all, let me say how much I have enjoyed hearing about the neuromorphic community, how it got started, and how their early ideas still have such an impact today. And for more about Carver's work, please go to brainsandmachines.net. Now, we welcome back our regular commentator, Professor Rolf Etienne Cummings from Johns Hopkins University.
Hello, guys. It's been a while. Nice to be back with you again.
So the first thing I would like to give to the listener is an example of what Carver has done. So they made transistors smaller and everything got better. He was talking to Gordon in the 60s, and then he was saying that the energy consumption got better as the cube of the scaling. So I just wonder if we have an example that today could compare to what they have done in the 60s so that we can clearly appreciate the greatness of what they have done.
Well, I would argue that everything that we have today in terms of the computers, the microprocessors, the fact that my phone has more computational power than my first academic computer, which was a Sun Microsystems machine that cost $26,000. I remember when I bought this as a first faculty member. Now my phone is way more powerful than it. That's an indication of how things have gotten better because of the scaling, because of the power consumption, because of the speed, exactly what Carver was talking about.
If I can go ahead, it might be a bit more philosophical at this point, but he said people are so stuck in the way they do things. He said, I suspect there will be something more interesting than just backprop. And he said, what's provocative, I think, neural network people are now up against way too much power. So now they're open to innovative approaches. So I was trying just to make a reflection there. So nowadays in the neuromorphic community, we think about making benchmarks and trying to let the people understand what we do and why it's good. And I totally see the value in it. But I'm jealous of Carver freedom and Misha freedom to explore new things as they were doing it. And actually, one thing that he pointed out is, in my opinion, or at least I interpreted it this way, is that probably we do not have to do such a constrained benchmarks, or we need to do exactly the things as it has been done with CPU or GPUs. Maybe we just need to do things differently, right? We just need to explore everything in a different way. So I wish we have the same freedom of just exploring rather than competing.
I'd like to say something on that. First of all, I think, yes, that exploring part is great. But as Carver points out at the end of the interview, it's also risky. And you have to be in a position in your career where you can take those kinds of risks. And for one reason and another, he was in a position where he could. Sometimes it cost him big money. Sometimes it worked out for the best. So it's not always easy to just go forward and do that. And also having that compelling commercial reason to be able to think about neuromorphic engineering, possibly for the first time. Here is a problem we need to solve. We have a compelling market that is beckoning us where we can make more money if we can solve this problem. To me, that's a really good thing. And that competition hopefully will push us as a field to do better. One other thing I wanted to say that sort of relates to this, what I really appreciated from what he said was that he came from an issue of parallelism, not just analog, which is what we often think of when we think of Carver and the original neuromorphic project. And that issue of parallelism, as an optics person, you can understand the parallelism is most of what I cared about when I first got into this field. It took me a long time to appreciate the spiking, to appreciate the analog. But the parallelism is still not being sufficiently exploited in any of the technologies that we use today. And that to me was really nice to hear. That was where he started.
Yeah, so I somewhat agree with you, Sunny, but one of the things I would argue is that, look, the GPUs are effectively parallel, right? In the sense that they are working on multiple different cores, computing data as they come through and applying what we used to call SIMD, right? Single instruction, multiple data type of applications as the data goes through. So there is still, a parallelism in those systems. And then when folks try to do it with FPGAs as well, again, exploiting parallelism there. But going back to your original question about whether or not exploration for the sake of exploration, as opposed to trying to meet some benchmark that some other field have set for us, whether that's the right way to go, I do think there's value there as long as we can demonstrate the value to the problem being solved, right? So he kept referring to the autonomous vehicle scenario as searching for the needle in a haystack approach, right? The haystack being the real world. So what is that needle? So defining that and then trying to say, hey, I built a system that explores the finding of that needle. And here it is doing it. And if it does it at, 1,000th the power of the GPU systems or the FPGA systems or whatever, that's a win. So we have to still define what that needle is. I guess that's what I'm trying to say, that we have to define what the problem, what the thing that you're going after. Once you do that, then you can explore, and find ways to do it.
I was just going to say that I think, though I accept that parallelism does exist in technology, I think it still hasn't been 100% cracked. And if you talk to people who work in these kinds of architectures, there are still difficulties in how you partition problems so that they work in a kind of seamless, power-efficient way, which is one of the reasons why we have so many problems with power today. So it's not just the underlying circuitry that's causing the problems. It's the way they're organized, and the communication between them is still not as efficient as it could be. And I think that will come with increasing parallelism, more micro parallelism. But I do accept your underlying point, which is that we are so far ahead of where we were when this project started back in the 60s and 70s that, perhaps I was a bit over the top at the beginning.
Yeah, I probably was just venting because at the moment I'm trying to benchmark as much as I can, to compete as much as I can, and I would like to explore more as a researcher. Maybe that is only the problem. So actually, the one thing he said is resonating with me a lot, and he said, isn't the images that are important, it's the action. It was referring, of course, to the dynamic vision sensor and the fact that making frames is not really the case for us. And again, it makes me think about internal representations, and we all rely on internal representation for our models. And I think, and I believe, the future will be completely detached from all of these internal representations that we think they're needed in our model, but actually we could use some spatiotemporal integration, using the time and doing something more rather than frames or something like that.
So, my perspective there is, I guess, contiguous, but yet departures a little bit from his perspective, right? So the fact that we can communicate not just changes in time, but also communicate edges, communicate objects, communicate information, if you will, right, in the scene. And that's the thing that's dynamic. That is what I think would be the bigger impact. So then going to something that's near to your heart, Julia, near to my heart, which is, attention, which is where you are now seeing something that is novel, that is different, that is unexpected. And that unexpected thing need not just be the fact that something got brighter or dimmer. So as I was listening to him, I was thinking, he's basically referring to saliency, attention, what makes it important for us to survive, to be able to know the difference between the lion and the giraffe, right? The giraffe might kick you, but it's generally going to run away from you. The lion might eat you. That's important. So it's that information that keeps us alive. So it's more than just time, I guess. Yeah, maybe that's exactly what you meant by spatiotemporal, Julia. I do think, again, I go back to this regularly, that the first person to build an artificial neuron was actually Paul Mueller, and he should be recognized for that in the 60s. And there were conversations between Carver and Paul in the 70s, that I think it was a bit missing in the discussion. The second thing that it was interesting to me was the foveon camera discussion, right? So he talked about the fact that it makes the best pictures and so on. But clearly the marketplace didn't think so. Right? So why? What was it about the marketplace? I don't think it was that it was more expensive to fabricate these chips. In fact, if anything, I would argue that it's probably cheaper because you get more pixels per unitarian, right? Because you get all three colors in one go. So what was it about the foveon system that did not make it a large-scale commercial success? And having been at the table where the Japanese and the Americans were fighting it out during the 2000s. Part of it was just industrial jealousy. I do think that there was some of that, right? I'm trying to protect my market, and so therefore, I'm not going to listen to the other approach because it might infringe upon my ability to sell my cameras. Then the other part was, there was some color bleeding between the different color layers, and that cause some people to look at the images and not think they are as great as Carver was indicating that they were. So that's a little bit of a twist there.
And just to add to that, also, it's just one of these cases, my understanding is, where digital just rolled over it, in the sense that digital pixels got smaller and smaller, and the aliasing effects became less and less important, and the signal processing was better. That I just wanted to say something about representations. As with everything, as I get older, I see more of the gray between the black and the white. And if you look inside the brain, you're going to see things that, even if they don't at first glance look like representations, that essentially they're going to have some sort of representational properties. I think that's almost inevitable. And so I don't think it's that we're going to do away with representations altogether. I think what we think of as being a representation is going to change. And then some of the tools that maybe we were able to use before that helped us understand how to use representations, we might be able to keep, and some of them we will not be able to keep because they're just not going to be relevant anymore. But I think it's just not going to be as black and white. And one of the things that I'm kind of excited about now, I don't know if I would have been 15 years ago, is the idea of this co-merging of the different technologies together, where you're getting the best bits of each one. And I'm seeing people who are having spiking neural networks with a little RISC controller next to it and a little this bit and that bit, and they're just mixing it all together. And maybe someday, as we've talked about in previous episodes, maybe someday we'll have some nice
perfect substrate, some universal substrate for brains, but I doubt it. And I suspect we'll always have some kind of heterogeneity when it comes to circuits and chips and chiplets and all these pieces.
I'm a big believer in diversity. So that's an example of diversity in computation.
I know we could talk about Carver Mead for another hour, but unfortunately there's no time. So thanks to Sunny for another great interview and Ralph for helping us putting it into context. In our next episode, Sunny will be talking to some of the main players at Innatera, a neuromorphic company based in Delft, in Netherlands. We hope you join us then.
That brings another episode of EE Times Current to its end. Thank you for listening, and thanks to our guest, Carver Mead. EE Times Current is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript along with direct links to the other stories we've mentioned and other resources. Thanks for listening.